Hello, team. As we take a little break from our on-site meetings, we thought we might put out a few videos going over our particular robot and some FRC basics, although some of you will have actually built or programmed some of the components that we'll cover. Not all of the team has had that experience of either programming the electronics or building the electronics or doing some of the mechanical components. So it's a good opportunity for each team member to review what you've done as well as share that information with your fellow teammates as we go over the robot and as we anticipate hopefully a continuation of our season. So welcome Ms. Nour, Mr. Ayoub, and me, Dr. James, will be walking you through some of the elements that you built this year.
Hello everyone, Mr. Ayoub here. Today we will be talking a little about 3D printing hardware and software. 3D printing has been a popular means of fabrication for some years now, and it is only growing in popularity. In our labs, we have been implementing 3D printing for 4 years now. It is an effective way to prototype or create immediately usable parts. We are able to create these parts through CAD, which stands for Computer Aided Design. We are able to create a blueprint of sorts, or a CAD file, that we can send over to a fabrication machine such as a 3D printer, laser cutter, or a water jet. In this example on the next slide, we can see a 3D model created by a student to hold our RSL, or Robot Signal Light. The RSL is a pivotal part of the FRC competition robotics, as it is an indicator to students, coaches, mentors, refs, and judges that the robot is on. As you can see, there is a progression in the model's shape. We start off with a preliminary sketch of the model and then extrude it. Extruding is the process of adding the 3D elements to the sketch, giving the drawing a z-axis. We then draw on top of our extruded sketch and extrude remove. This creates holes inside of our sketch. We now have an RSL mount.
NEO motor is the first FRC legal brushless motor. It offers an incredible power-to-weight ratio compared to existing FRC motors. The NEO has a similar performance characteristics and matching mounting features as the SIN motors. As you guys know, we use this on our robot to drive the robot using 4 wheels. Also, we're using 2 of them on the actuators to control the elevator arm. NEO works with the SparkMax controller, which we will talk about next. SparkMax controller is what we use to control different parts of the robot, like the wheels and the elevator arm. SparkMax include advanced brushed and brushless DC motor control in a small and easy to use package with PWM, CAN, and USB connectivity. As you guys see in the picture to the right, the yellow-green wire is the CAN, and then red-black wire is the PWM. Do you guys know which one we use? We use the CAN wire because it's more advanced and easier for wire management, which is important to us as a team. Also, CAN uses ID and network frames to send information to the green and yellow wire. Each CAN will receive information based on the code. There are different colors on the Spark controller to indicate the status of the controller. The color magenta shows a valid signal, and then that's what we're looking for.
This was certainly an interesting part of your robot build this year. This was what we called the dumper system, and it was that idea of an accumulator or what we might call a hopper, something that could hold power cells and then hopefully dump or remove them or expel them into the actual local scoring opening. And as you know, most of you know, the reason that we went with this sort of dumper system versus some type of intake system or maybe a shooter was that we did experiment with the latter two. However, we had a bit of a weight issue. The robot found itself probably at around 135 pounds, with regulations being at about 125. So a few of you were involved with going back to the drawing boards. All of you were involved with the idea of rethinking this system. So this is what we used, some of the materials we had around the lab were the idea of the kind of corrugated plastic. That corrugated means that it has the gaps in it, so it kind of creates an open gapped plastic sandwich, much like a piece of cardboard, only a little bit larger. So those were approximately maybe around a quarter of an inch or a half of an inch by a half of an inch of openings, and that creates this very lightweight yet semi-rigid plastic element. And that's what the majority of the dumper system is made out of. Now, coupled with what you built was the X-bar. As we know, X-bar is actually T-extrude aluminum, meaning that it was hot aluminum that was like a piece of spaghetti or pasta was pushed through a shape or a mold, and that creates an extruded piece of aluminum, and it has the nice slots in it, and we can use those number 10 bolts and nuts. And remember, that's why we always say, oh, well, hand me the 3/8 wrench or the 532 driver, and that's how we put that together using the number 10 nuts and bolts. They fit directly into that X bar, and if you remember, Captain Imad showed some of that in a video that he did earlier. And then also we, of course, motorized the front hatch of this dumper system using a servo. Now, originally we used a small electronic actuator, which was very fun and interesting to program. However, that actuator, if you remember from the final days of our build, was actually quite slow. So we wanted to find something a little faster so that we could increase our cycle times. Cycle times are when we go back and forth collecting and dumping power cells. In order to do that, we wanted that hatch or that front hatch to go up and down faster. And so we use this idea of kind of an oversized servo, and we'll talk a little bit about what a servo is in just a moment. Just to go over the positions of it, of course, the accumulator here, the dumper system could hold 5 power cells, which was the legal limit, 3 power cells when we actually were in on at the very beginning of the match. We could open at 45 degrees. This was all, of course, teleoperated by the operator, the assistant to the driver. And 45 degrees, what we calculated would be the opening for a human player intake. And then 100 degrees, which is past the 90-degree mark, so approximately over 100 degrees, meaning that straight up and down, the position that it's in the picture was when it's holding the 5 power cells. 100 degrees from that is 90 degrees plus 10 degrees, and that's what it would look like when it was actually dumping the power cells into the low-scoring goal. And that was the whole idea of it. And we also would have that open if we went to try to spin the control panel. Viewing a few of the components for the dumper, again, we were using X-bar, as you can see in the graphic here, and I think that's Zachary and Imad placing in the X-bar on one of our upgrades. That's when we were trying to find out the optimal height for the actual dumper system, remembering that you needed to do a low score of about 18 inches and the human player dump height of about 24 inches. And that was very tricky because remember you had that front door. We did use a series of brackets. Again, these are all adjustable and are adaptable to the number 10 bolt and nut system, and then work very well with the extrude, the X-bar. Plastic was the corrugated plastic, and that was a corrugated plastic. That was that idea of a kind of a cardboard-like shape, but in a plastic material, semi-rigid, but easy to manipulate. So if we needed to cut it or reshape it, it wasn't hard to do. The servo you're seeing here is often referred to. You can kind of read it in the picture off to the right there. It says the mega scale servo. And the idea there is it's a little bit larger servo, so it had the strength in order to flip or to pivot that front end of the dumper, which was kind of that trap door. You see that it says it's 160-degree modifiable, but as we could see there, it was really about 180 degrees, and we're only using about 100 degrees of its current settings. And it talks a little bit about the connected wire there, about 11 or 12 inches in length. You remember that. That was a PWM cable that you can see there wrapped around the servo in the picture. It contains 3 separate wires. There is what's a ground wire, positive wire, 6 volt, and then a signal wire, which actually pulses using what's called a pulse width modulation to tell the servo how far to go or to run forward or run backwards until we either say stop running forward or backwards or to a specific setting. Now, I won't go into all the specifics. We can go into that detail a little later, but one interesting thing you see here is it has a stall torque of 247 ounce inches at 4.8 volts and a little more than that at 6 volts. So if we hit it with the full 6 volts, it has more than enough strength to lift our little gate. And you can see there that it was also helpful for our weight issues that we were having because it's only about a little less than a half pound at about 5.36 ounces. All right, let's take a quick look at programming a servo. So this is inside of the Visual Studio Code interface, and what you want to do is, as with anything, you want to import a library. So a few of you have done this already. Some of you have not. So this is just an introduction to sort of how we would go about programming this, or how we did program this inside of your particular um, servo example. So what I want to do is import the servo library. That's how we would begin. I'll kind of zoom in on that so you can see it. This is an important first step. This allows us to now utilize some of those library objects, if you will, that we can now build code from. So you'd come down then to your robot extend iterative robot, and this year it's called timed robot, so it's a little bit older version, but you can kind of get the gist of it. So we're going to say we're going to create a private variable. So that private means that it's local to this main function that's happening as the robot runs. This is in a particular Java um, uh, page called the robot.java. So this is compiled, and then this is the main actual Java compiled piece that is run during the contest. So we're going to say private, and you just give it a particular name. So let's say if you were going to say, oh, I want to create a servo. So we're going to use a servo, and then we'll call it my servo. And now this name is something we're just making up. It's called my servo, and that's how we're going to begin. So now down in robot init, we need to go ahead and construct that. So we've declared it. We said, hey, we're going to create a servo object. That's what we see in line 28. Now we're going to go ahead and instantiate it, or in this case, we're going to construct it. So we do that by just saying something like my servo. So you'll see that it's using IntelliSense, so it's trying to help us as we type, equals new, so we use the keyword new, and then we're going to say servo. So this is what we're trying to create. Now you can see here in the list, if I just hit enter, it says what's the channel. Now if you're looking at the right side of your screen, you see that there's actually a picture of the RoboRio, and we're going to plug this in to the PWM spot 0. That's the first one on the list, and this is where we now can access that. So we have it in the actual RoboRio physically plugged in using the PWM open slot 0 with the ground wire, the black wire being on the right, and the positive wire center, and the signal wire on the far left, depending on, of course, your orientation to the Rio. The only last part to actually make this move, now it takes a little bit to get it precise, but to get it to move, if we went down to teleop periodic, that's where you're now controlling it, we're going to go ahead and just say, okay, my servo, remember it knows what we have there, and then we're just going to say set. And it's looking for a value between 0 and 1, 0 being its furthest left or counterclockwise position, and 1 being its furthest right or positive clockwise position. So again, our particular servo is limited currently at 180 degrees. It can be set to 360 degrees, so it could be fully continuous, but currently ours is limited to 180 degrees. We need about 100 degrees, so we'll kind of manage that ourselves in just a little bit. But for now, let's just say 0.5. And what do you think that would actually make the servo move to? If you guessed halfway, you'd be right. So a halfway of 180 degrees is 90 degrees. We could add a little more to that, maybe 0.7, and we'd probably get that position around 110 degrees, which is what we want, 100 degrees to 110 degrees. Remember, we're going from straight up and down to this forward dumping position. And really, that's it. The very beginning of creating or making a servo work that's plugged directly into the RoboRio is this code that you see here. Okay, team, that's it for our first session. We did cover a few wonderful items which were on our robot this year. You created that a great example that Mr. Ayoub went through, where you created the robot signal light, the RSL holder, in a 3D program OnShape, and then transmitted that to our 3D Ender, 3D printer, and we're able to create that in that awesome green filament. And that now was positioned, of course, in the robot tower, in the back tower of the robot, and was effective in creating a wonderful signal location. So great job on that. The next thing that Ms. Nour walked you through was the concept of our main motors, and those were the brand new brushless motors, the Neo motors from last year, that we now upgraded in a few spots. We use them in a couple locations, including the big climber motors, the 400 to ones, and also our drive chassis. So it inhabits all four of our wheels in the mecanum, independent wheels, and that's using the brushless motor. And of course, they're powered by the Spark Max motor controllers, which she identified as being on a CAN network, which was great. We'll go through the programming of those at a later session. And then my section, we talked a little bit about the dumper system or dumper creation that we had, the mechanism. And we talked about the physical elements as well as the electronic elements like the servo itself and some of the programming that goes into that. So hopefully you enjoyed this session. Let us know if you have any feedback or questions. Some of you, it's going to be very familiar. Those were things that you worked on when building your robot. But for some, that's our new concepts. And please share with each other thoughts and considerations as we go through that. And thank you for listening. We want to put out a number of these while we're out of face-to-face contact. That way we can keep thinking about robotics and hopefully building our knowledge to prepare for whatever our next season events will be. Thank you so much.